In the previous videos, we developed the 2D continuous formulation, followed by the discretization of the spatial terms, and then finally the full unsteady two-dimensional discretization for our problem statement. Now we need to look at the elements and the basis functions. So in the first case, we're going to choose triangles as our elements. Why triangles? Because they're easy to fit to any complicated geometry. If you think about a geometry with curves, you can easily understand that it's easier to fit a triangle or a number of triangles into that space than it is to fit quadrilaterals. So let's look at the numbering scheme for our triangles. We will use both the letters I, J, K and the numbers 1, 2, 3. So for our triangle, we have node I, node J, and node K. We're also using 1, 2, and 3. Note that we are using the labeling in a counterclockwise rotational way. This is the convention. It will ensure that we have positive values for area, but it will affect the sign associated with the terms that are in the basis functions. So you need to be sure that you are using a counterclockwise direction for your node numbering scheme. So now we want to build out the basis functions. So we know that we are working with linear functions in this particular course, and we want a piecewise linear function. So what we want is a function where n sub j as a function of x sub I, y sub I is going to be equal to 1 when I is equal to j and 0 when I is not equal to j. And furthermore, because we know that we want a linear polynomial, we know that our basis function will have the form n sub I is equal to a sub I plus b sub I x plus c sub I y. So let's go now to our whiteboard and derive the full expression for the basis functions. We defined our triangle. We labeled it I, J, K, using a counterclockwise direction for our labeling. We said that our basis function, because it's linear, was going to be at its very simplest a sub I plus b sub I x plus c sub I y. And this satisfies the requirement that n sub I is equal to a function of x and y. And it satisfies, it's a linear polynomial. It's the simplest that we can find. Now we need to derive expressions for our coefficients, where the coefficients here are the a sub I, b sub I, c sub I. Let's go ahead and derive expressions for our basis functions. And in order to do this, it first means that we need expressions for the coefficients. So let's look first at a of I, b of I, c of I. So what do we know? Well, we know that n sub j of x of I, y of I is equal to 1 if I equals j, and 0 if I does not equal j. We combine that with n sub I equaling a of I plus b of I x plus c of I y. And when we combine those two, we can set up a system of equations to solve for our a of I, b of I, c of I. So let's look at the very first one. 1 times x of I, y of I. When that operates on the vector a of I, b of I, c of I, we know that it's equal to 1. But when we have x of j, y of j times that vector, we have a 0. And the same is true for k. So now we have a system here and we can solve for our coefficients. So you solve the system using our usual algebraic techniques. When we solve the system, we have, I'm showing you here an intermediate product. So this is x of j, y of j, x of k, y of k. And that's going to be over the determinant of C, where C is the 3 by 3 matrix that we started with. And we can expand that or simplify it by saying that this will be x of j, y of k minus x of k, y of j over the determinant of C. Likewise, we will have an expression for b of I that's equal to y of j minus y of k over the determinant of C. And C of I will be equal to x of k minus x of j over the determinant of C. So now we need to compute the determinant of C. And I'm sure that you're thinking to yourself, yes, we'll just do that algebraically using standard algebra techniques. But I want you to also think about it in terms of a geometric solution. Let's look now at a geometric perspective of the determinant of C. So one way to think about this is that this is effectively a cross product. Consider two vectors, and we'll call them u and v. And if I do the cross product, I essentially have something that now looks like a rectangle. But let me call out, I'm going to put a dashed line here halfway through the rectangle. And let me call out this area because this section that I'm highlighting here in blue, this is our element. And if that's our element, then this section here that I'm highlighting in the cross product is 2 times the area of our element. So that says that with the determinant of C equal to the cross product of the two vectors, we can also say that it's equal to 2 times the area of our element. So if the determinant of C is equal to 2 times the area of the element, then what we can also say is that A of I is equal to x of j, y of k minus x of k, y of j over 2 times the area. And we can say that b of I is equal to y of j minus y of k over 2 times the area. And we can also say that c of I is equal to x of k minus x of j over 2a. So now, just as we did, or similar to what we did with our defining our element lengths with the 1D case, we've got some definitions that we're going to bring out. So we are going to define delta y of I equal to yj minus yk. We're going to define delta x of I equal to xj minus xk. And when we substitute those in, that means that b of I is delta yi over 2a, and c of I is delta xi over 2a. And furthermore, n sub I is then equal to 1 over 2a times xjyk minus xkyj plus delta y sub I times x minus delta xi times y. Recall that the discrete formulation required not just the actual function value, but it requires the derivatives as well. So we need the derivatives and we need the actual basis function. And we'll need it also as the weight function. So starting with the fact that we have ni, we've defined it as ai plus bix plus ciy, and that we now know that that is also equal to 1 over 2a times xjyk minus xkyj plus delta yix minus delta xiy, we can use equation 1 to say, when we're looking for di dx, dni dy, we'll use equation 1 to say that this is equal to bi, and the derivative of ni with respect to y is equal to ci. We'll use equation 2 to further say that this is equal to delta yi over 2a, and the derivative of ni with respect to y is equal to minus delta xi over 2a. And now for node I, we have an expression for the basis function and the derivative of the basis function. Likewise, the weight functions, since we've made the Galerkin approximation. If we follow the same analysis for nj, we will have a of j will equal a minus, this is again because now we're again starting from that second column, xiyk minus xkyi over 2a. And our bj is going to equal y of k minus y of I over 2a. And our c of j will equal x sub I minus x of k over 2a. As we did before, we're going to define some expressions. In particular, we're going to define delta y of j is equal to y of k minus y of I. Delta x of j is equal to x of k minus x of I. And that means that what we will have here is that bj will be equal to delta y of j over 2a. And cj will be equal to minus delta x of I over 2a. Okay, again, remember that our discrete formulation needs both our actual basis function, and it also is going to require dnj dx and dnj dy. So those are going to be equal, just as before, to delta y sub j over 2a, which will be equal to b sub j, and minus delta x of j over 2a, which was equal to cj. Before we talk about k, let's look at the pattern that's emerging. So we have a pattern that we're starting to see. And that pattern looks like n sub I is equal to 1 over 2a times xj yk minus xk yj plus delta yix minus delta xi y. And j is equal to 1 over 2a x k y I minus x I y k plus delta y j times x minus delta x j times y. So our delta y sub I is equal to y sub j minus y sub k. Our delta x sub I is equal to xj minus xk. Our delta yj is equal to yk minus yi, and our delta xj is equal to xk minus xi. Just for completeness, let me draw the triangle again so that we can think about what we're seeing. So we've said that this was I, j, and k, and that we're using counterclockwise order. So when you look at this, you can see that you're going from j to k in the case of I. So if you're standing at node I, here's our node I. In both cases, you're going to go from j to k. If you're standing at node j, you're going to go from k to I. So this is the counterclockwise piece that we're seeing. And in each case, the delta x terms that fall out of the system of equations that we solved within that matrix system, they come out to be working the other way. So they end up with the minus sign. Based on looking at this, what do you expect that we will find for our n sub k? So based on the pattern that we've already seen, the pattern suggests that n sub k will be equal to 1 over 2a times x of I, y of j, minus x of j, y of I, plus delta yk times x, minus delta xk of y. And we expect that delta yk is equal to yi minus yj, and delta xk is equal to xi minus xj. So now we have expressions for the basis functions. We have expressions for the derivatives. We're ready to talk about the implementation in code. That's our next step.